Hello, this is Chuck Ridgway, Automation Technology Manager at Horner. Thanks for joining us for another Tuesday live stream. But not just another Tuesday live stream, it is a CPU summer. And this summer we have great content where we're giving you all you need to know about the new Horner modular controllers, the new CPUs that we're releasing this summer. And most of our content thus far has been focused on the CPU250. A great new controller that doesn't feature a screen, but has a ton of great built-in I/O. And we're going to be covering that today once again. Now, if I look a little sunburned, it's because I am. I just got back from a big bicycle ride across Iowa. It is RAGBRAI is the name of the event. And this year, I believe there are around 20,000 riders. It's pretty crazy. Every year, there's a unique route across Iowa, and this year it was about 400 miles or so, and there were a couple days where there was a heat index over 100 with unfavorable winds, and that made it very tough on those days. But most days were just a ton of fun with really good riding, and the winds weren't in our face, and I had just a wonderful time. But anyway, enough about that. Let's get to today's topic focused around the CPU250, and that is migrating to the Micro CPU250 from the RCC. Now, the RCC is an existing line of controllers that don't feature screens, just like the CPU250. And today we're going to tell you how you can migrate from one of those products to the CPU250. And the reason that's important is because at some point relatively soon, the RCCs are going to go to mature and then ultimately to obsolete status. So you will want to replace them with the CPU250, at least for new installations. Of course, your existing RCCs in the field should give you great, lifetime of usage, with years and years to come. All right. So without further ado, let's go ahead and break down today's topic. Today, we're going to start with a quick review of the CPU250, and then we're going to go through all the different RCC models. We'll talk about migration strategies for moving your application over from the RCC to the CPU250. We'll go through all the different conversion steps, and then we'll show you those conversion steps in Cscape as part of a demonstration. All right, here we go. The new micro modular controllers are indeed part of the Micro series, which previously only included all-in-one controllers and now includes modular controllers. The new modular controller CPU250 is probably the star of the new CPUs that are being released or that have been released this summer, as they feature all the things you'd expect from a microcontroller, all the same connectivity, and things like micro SD. They also feature USB-C for programming, which you'd expect out of a brand new product, and they have the ability not only to have all kinds of great built-in I/O, but also to have additional I/O plugged directly in the side of them using just standard OCS I/O modules. And they support all the standard protocols that you'll find in any micro OCS controller. Now, I mentioned earlier that all that great built-in I/O, there's 34 built-in I/O points in total, including 8 of which that are flexible between digital and analog. So lots of great I/O built in to the CPU250. Now, let's take a look at the RCC Controller Lineup. These are a series of models that have been released over the years, starting with the RCC 972 and moving its way through the RCC 6512. So there are currently 5 models in the lineup, although the RCC 2414, I believe, has already been obsoleted. But some of you may have an application out there that's using that particular controller, so it's going to be covered in today's program. All right, let's start going model by model to what each RCC has to offer, so we have a good feel for what we need to convert to the CPU250. All right, so most of the RCCs have similar features. Micro SD slot is common, at least one Ethernet port, at least one serial port. Those are all pretty common. DC power input. The actual voltage range may vary a little bit from model to model. They all feature recessed push buttons for starting and stopping the controller or loading a new program from micro SD. They all have status indicators for run, OK, and power, and some of them also have additional indicators for network activity, all right? And then where they really vary, for the most part, is in their I/O complement. How many digital ins and outs and how many analog ins and outs they have. Another area where they vary is also in the amount of programming resources available, or the logic resources probably is a more appropriate way to put that. How much logic space, as well as how many retentive word type registers and retentive and non-retentive bit type registers. So for each model as we go through them, you're going to see a table in the upper right hand corner that shows those differences. So the RCC 972 was the first one that we released, and one thing that's unique about that particular model is the fact that the RCC 972 doesn't have a real-time clock or a battery. So that was a requirement for the particular OEM that we designed it for, even though we can sell it to anybody. So that's something to be aware of with that particular model. Okay, moving up to the next model, we've got the RCC 1410. Okay, some of the big differences here, beyond just the I/O complement differences, are the fact that the RCC 1410 has a lot of available registers as well as program space. So it's got 50,000 %R registers. It's got 32,000 bit type registers, half of which are retentive. And it has 2 megabytes of logic space. So it's really got a lot going for it when it comes to memory. But keep in mind, the new CPU250 matches that in terms of all those different parameters. So again, you'll be able to see as we go through this presentation today that the CPU250, part of its specifications were developed so that it could easily replace these RCCs moving forward. From an I/O standpoint, the RCC 1410 has 14 digital in and 10 digital outputs. It does not feature any analog. Now let's look at the RCC 8842. It's identical to the 1410. The only difference is the I/O complement. It has 8 digital in, 8 digital out, 4 analog in, and 2 analog out. One other thing I forgot to mention about the RCC 1410, as well as the 8842, is they also do have LED indication on their terminal strips, whereas any RCC model you'll see that just has green terminal strips for the I/O instead of the black ones. Those green terminal strips don't feature LED light pipes, so they don't have LED indication, whereas the black terminal strips do that are used on the 8842 and the 1410. Okay, moving up to the next model, the RCC 2414. Now this one is a little unique. This one is really used, I believe, in quite a few different lighting applications, but it was ultimately obsoleted. So if you've got one of these, there's a decent chance it may be being used in a lighting application. What makes the 2414 different is the fact that it has 2 Ethernet ports, okay, instead of just one. And from a serial port standpoint, it has 2 RS-485 ports. So that's really 2 of the things that make it unique. The last thing that makes it unique is its support for USB. So it's got USB for programming, as well as a USB host port for a flash drive. So that's the RCC 2414. The last model we're going to talk about really is a coprocessor, that we consider it a coprocessor. And this is a very high volume product, but it is primarily used for high-speed counting. So if you want a remote high-speed counter, this is the product that most of our customers use, okay? And that is an RCC 6512, which has a ton of high-speed counter capability. It has actually 12 high-speed inputs that can be used for high-speed counting, encoders, up counting, down counting, etc. And then it also has some analog built in as well. So it's a very versatile product, but it has a very limited number of resources from a programming standpoint because it's really intended to be a coprocessor. Again, due to its incredible high-speed counter capabilities and its limited CPU resources. Okay, so that's the lineup of all the different RCCs. Now let's take a look at how, moving forward, you can replace these RCCs with a CPU250. So 5 different models of RCCs to be replaced for the most part with one CPU model. Okay, so what are our migration strategies? Well, first of all, most of the models can easily be replaced with a CPU250, which I've mentioned a couple times already today. Because the CPU250 has plenty of built-in I/O that can cover really any RCC model that exists out there. And the CPU250, even though the RCC has a lot of capacity for, most of the models have a lot of capacity for programming in terms of programming space and register space, the CPU250 also matches that as well. So again, that's why moving from most models to the CPU250 makes a lot of sense. Now, in a couple of cases, you may find that you want to transition to a CPU300 instead. Now, we haven't covered the CPU300 yet this summer, but it is coming next month, actually, which we'll talk about at the end today. So in a couple cases, if you really need the 2 Ethernet ports, or if you really need the extensive high-speed counter support, as well as, plus or minus 10 volt analog outputs, in these cases, you might want to transition over from the 2414 or the RCC 6512 to the CPU300 that we're releasing later this summer. But again, even these models, in a lot of situations, can be replaced nicely with the CPU250. All right, now let's talk about what we actually have to do besides just ordering a different part number to do the actual migration. What do we actually have to do? Well, let's start by talking about physical migration. What does that look like? Well, from a physical size standpoint, the RCCs and the CPU250 are virtually the same size. So they have the same footprint on your DIN rail or in your enclosure. So that's good. That makes things really simple there. From an I/O wiring and a power wiring standpoint, if you're following the traditional approach of having a field terminal strip inside your enclosure, then you're just going to need to rework that wiring, okay, from the field terminal strip to the terminal strips on the CPU250. Because obviously, even though a lot of the signals are the same, the I/O terminals aren't in exactly the same location. So you will have to redo that wiring. But that shouldn't be too bad. Now, from a serial port wiring or an Ethernet wiring standpoint, the good news is the pinouts have not changed. Okay, there may be additional signals on the modular jack, for instance, that handle serial ports, but the signals that were there before for your RCC application are still there in the same location for the CPU250. So that should be pretty straightforward. If your communications cables, your Ethernet patch cables, your serial port cables, if they are of sufficient length where you can move them from where they were with the RCC to where they are with the CPU, then no changes have to be made there as well. Okay, so that's some of the physical changes. Now let's talk about CAN. There are some pretty big differences with CAN, mainly the fact that even though the CAN wiring was not standardized across all the RCC line, it was always using a terminal strip. Whereas with the CPU250, it uses an RJ45 port, which is a modern way of handling CAN. So there's a couple ways of transitioning there. First of all, if you are using traditional CAN wiring, the traditional Belden CAN wiring, and you would like to connect those same wires to the CPU250's CAN port, well, you could use an RJ45 to terminal strip cable. That is an option that you do have. Or if all you're going to do is, let's say you've got the CAN wiring going to the field terminal strip inside the enclosure, and you want to make that connection to the CPU250, well then from the field terminal strip you can just run, let's say, a Ethernet patch cable chopped off on one end, and then you can connect 3 terminals, the CAN high, CAN low, and the CAN ground, to your field terminal strip, to the appropriate terminals, and then you're good to go. Now, what about termination? What about that? Well, with the RCC, if you're using CAN, then and the RCC is on the end of the network, then almost certainly you've got a physical resistor that's plugged in at the end of the CAN network on the RCC, if it's at the end of the network. Well, you don't really have an easy place to put a physical resistor with the CPU250, But the CPU250 does have software-enabled CAN termination. So simply by turning on a system bit, you can turn termination on, so you don't have to mess with a physical resistor. So that's another option there. Now this particular slide here shows the pinout that you can use in those two scenarios I went through previously. One scenario is where you chop off that Ethernet patch cable and just wire up 3 pins from your field terminal strip into the CPU250. The other scenario is where you use a RJ45 to terminal strip breakout adapter like I've got shown on the screen there, and then you can see the pinout that's required in that scenario. Okay, so that the differences in CAN physically are a little more significant than they are with the Ethernet and the serial ports. All right, now let's talk about I/O mapping. Now, from a basic I/O map standpoint, there really aren't any significant differences between the RCCs and the new CPU250. Let's go through the differences that do exist. Okay, so there's a feature that a lot of customers don't always take advantage of, and that is there is a digital input digital input register, I should say. It's actually a %I bit. That will turn on if you have a short circuit on one of your digital outputs. That's available pretty much with just about every OCS model that's out there. A lot of people don't take advantage of it. Well, in the case of the RCCs, that indication of a short circuit comes on typically with %I16, although if you're using one of the models, I believe it is the RCC 6512. If you're using that model, then the indication for short circuit is I32. But in either case, in the CPU250, that bit is I25. So if you are using that short circuit indication bit, you will have to remap that one. And then another case where remapping may be required is in the case of analog outputs. If you are using voltage analog outputs, you may have to do a remap of your AQ registers as well because of the way that works in the CPU250. But we'll cover that in our demonstration. All right, now let's go through what you need to do in Cscape step by step when you're going through the migration from the RCC to the CPU250. The first step, as always, you want to archive your existing RCC program and then make a duplicate of that program so that you're starting with a copy of that program as you make programming changes. Okay, that's always critically important. All right, and then once you're in the new program, all right, then you're going to go to the hardware configuration and you're going to change your controller model from whatever RCC you are using over to the CPU250. Then you're going to go to the local I/O tab and you're going to do whatever configuration is required. And most of your configuration, and you'll see this in the demonstration, is probably going to be in the flexible input section and the analog output section of the CPU250, because that's where your analog is configured. The RCCs didn't have many options for the most part with their digital inputs, all right? They, for the most part, did not support high-speed counting, again, except for the RCC 6512, which is a high-speed counter coprocessor. All the rest of the models didn't do any high-speed counting at all. So there's not much configuration that'll be required there. It's all going to be on the analog side. And then the remainder of the changes in your logic program are probably going to be related to your analog outputs, because if you're using any voltage analog outputs, the voltage analog outputs are mapped in a different area with the CPU250 as compared with the RCC. So you'll need to do that remapping from both a register number as well as an I/O names standpoint. All right, and then finally, it's just a matter of saving your program and downloading and testing. So really pretty straightforward. There's not that much to it. When you think about, maybe the tens or even hundreds of K of ladder logic that you may have in your RCC, there's really not that many changes you'll need to make. Okay, so without further ado, let's get right to demonstrating how you would make these changes, at least the ones that you would make in Cscape. Okay, let's do a conversion of an RCC program to the CPU250. So we start by archiving and then copying our existing RCC program. So let me go ahead and copy and paste that program. I'm going to do a quick rename. Okay. Whatever you want to rename it. And then that's the program we're actually going to open. Okay, which is the one we just created that was a duplicate. All right, so before we go in and do the conversion, let's explore what the RCC configuration currently looks like. Okay, so we'll go into hardware config. It's configured for an RCC 8842. Let's go take a look at the local I/O and see how that's configured. Okay, so digital inputs, everything's at default with positive logic. Digital outputs, everything is also at default. Analog inputs, it looks like we've got 2 4 to 20 milliamp channels and 2 0 to 10 volt channels with a filter constant of 3 for some digital filtering. On the analog output side, we've got a 4 to 20 milliamp channel, a 0 to 10 volt channel, and we're going to 0 when the controller is stopped. Okay, so that's the configuration we want to match in our CPU250. All right, so now back to hardware configuration. Now changing our target to the CPU250. Okay, now that we've done that, we can go back into local I/O. We can see the picture's different. The defaults for digital inputs, nothing to change here, still positive logic. Defaults for digital outputs, nothing to change there. Now here, we're going to have to manually make these changes because the analog settings don't follow through automatically, so we have to make those manually. All right, so I'm going to set my digital filtering to 3 because that's what it was before on the RCC. My first channel is going to be analog, 4 to 20 milliamps with scaling of 32,000. My next channel is the same, 4 to 20 milliamps, scaling of 32,000. My third channel was 0 to 10 volts, again, scaling of 32,000. How do I know the scaling was 32,000? Well, that's the only option that you have for the RCCs. They just by default are 0 to 32,000. Okay, so now my analog input channels all match what they should. Got my filtering, I've got my signal types, and I've got my data range. Okay, so that's done. Now let's take a look at the analog output side. I had one 4 to 20 milliamp channel, and again, 0 to 32,000 because that's all the RCC supports. And when the controller is stopped, I want to be at 0 or minimum, if you will. Now I can't configure the second channel here for voltage because if you want voltage, you have to go down here to the 5th channel, okay, the 5th through the 8th channel. So 0 to 10 volts, 0 to 32,000, and halt state of minimum is what I want, but I have to note that my second analog output is no longer AQ2, my second analog output is now AQ5. So I'm going to have to make mapping changes in my program to change AQ2 to AQ5 everywhere in my program. All right, so I will prepare to do that now. Okay, so I'm done with hardware configuration. Now I'm going to go in and replace every instance of AQ2 in my program with AQ5. Now, if I have more than one instance, then the easiest way to do that would be to go to the Edit menu and the Replace option, and I would do a Find AQ2 and replace it with AQ5. Okay, and hit Replace All. It tells me how many have been replaced. So that's good. Now, if I'm using register-based programming, I'm going to have to also do a change on my I/O name because I lost my I/O name when I made that change. So I go over here to I/O name, right-click, hit Edit, find AQ2, which is the old I/O name that now needs to be AQ5, make that change, hit OK and OK, and now I can see that I've got my I/O name along with my proper analog output register. Okay, now if by chance we're using the short circuit indicator, which is either going to be I16 or I32 depending on my RCC model, then I need to change that to I25. So I know that I've only got one instance of this here in my program, so I'm going to go ahead and change it from here. But again, if I have multiple instances, I'm going to have to change them all manually. Again, I lost my I/O name, so I need to go back here to the I/O names area. Okay, find I16 and change it to I25. All right, again, I could have done the search and replace technique. That's also totally valid, but I wanted to show you the other way of doing that by changing it manually here. Okay, so now that change has been made. And the only other change I might want to make would be if in my RCC I was using a physical CAN termination resistor, and in my CPU250 I'm going to use a software-enabled termination resistor that's internal to the CPU, then I need to add one more rung of logic to enable that software-enabled termination. So let me put a comment in here. Enable software-enabled CAN termination. Okay, that's what I'm going to be doing with one more quick rung. Then I'm going to need to put an always on contact here. Again, I'm demonstrating register-based logic today because most people doing the conversion probably have an older register-based logic program that they're working on. Okay, and then the SR for software-enabled CAN termination is SR 152.4. It does not have a default I/O name, so I'll go ahead and name it now. All right, and there we go. So that is the final change that I should have to make, that I need to make in this particular example. Your actual example may be slightly different, but this should give you pretty much what you need to know. My last steps are going to be to save the program, the modified program, of course, and then download and test the result. That does it for our content for today. Don't forget to sign up for OCS training. We've got 2 courses left for the year. If you'd like to see some of these new products in person, check us out at one of these trade shows. We're all over the South. We're all over the Midwest. We'd love to see you. If you'd like to interact with us online, you can do so on our website, on our YouTube channel, or on LinkedIn. August is going to be a big month. We've got our new CPU300 launch webinar that'll be coming up on Thursday, August the 21st. You'll have to register for that because that uses our Big Marker webinar platform. So that's a huge event. Next week, from a live stream standpoint, I'm actually taking the week off, but we've got 3 live streams planned for August, the 12th, the 19th, and the 26th, with lots of good content, much of which is focused on these new CPUs. If you haven't subscribed to our channel yet, don't hesitate to do so. It doesn't cost anything. And if you choose notifications when you subscribe, you'll be notified every time we go live or every time we post a new video. Now, I've got the week off next week, mainly because I've got another bike trip. I'm going to be in northern Michigan this time. I'm hoping for a little cooler temperatures. But you might say, well, dummy, you're going bicycling in July. What do you expect? Well, the temperatures in Michigan should be a little cooler than they were in Iowa last week, although I had a great time in Iowa. All right. So whatever you're doing, whether you're going on vacation like me or whether you're working, get out there and do some good.